Yeah. Yes, it looks good.
Presentation.
Okay.
Wait, sorry. Just 1 second, please. I think minimize.
I think it looks good. Okay.
Mhm.
All right. The next talk is by Yulia Yeshova from MSU, and she's speaking about effective static and quasi-static properties of periodic inhomogeneous media.
Thank you very much. First of all, I would like to thanks the organizer for organizing this conference and for the invitation. It's my pleasure to give a talk, and I would like to continue topics of Sasha because this is joint work with Alexander Kiselev and Kirill Cheretnichenko, and I would like to discuss in details non-standard properties, non-standard metamaterial properties of um, high contrast media. So let me please start. This is standard picture. Maybe let's start with high contrast setup. So as Sasha mentioned, uh, let's consider periodic media. It consists of components of with very distant properties. Say epsilon square it's a critical case. Um, uh, for that example, we will consider soft matrix, stiff matrix, sorry, with soft inclusions. So these blue inclusions are soft, and a symbol of the second order operator on the inclusions are of the order epsilon square, and the symbol on the stiff component, which is green, is of the order 1. So this case uh, is not the same as a moderate constant homogenization, and the effective. So we are looking for the effective operator for the effective properties of this periodic media when the period epsilon tends to 0. And this operator will have first of all, it will have a band gap structure spectrum. And moreover, it may possess non-standard properties. It may have non-standard properties, metamaterial properties, and I'll show such examples. For that operators, like the main difference from the moderate contrast, the main difference with the Birman-Susina case is that the eigenvalues, non-zero eigenvalues of this operator don't separate it from 0. So in the vicinity of 0, in every vicinity of 0, it's always possible to find an eigenvalue of this operator. Okay, and we will study the most simple example. It's also possible to find exactly same effects in the two-dimensional cases, three-dimensional cases. But for simplicity in the talk, we will consider quantum graphs. Quantum graphs, it was proven that the quantum graphs serve as a limiting model for waveguides, for thin structures like of that kind. That can consist of thin tubes and these vertex areas. Thin structures are studied by many mathematicians, in particular Peter Kuchman and his student Zeng. They proved convergence of the PDEs on this graph to the ODE on the limiting, like underlying quantum graph, with a special matching condition at the vertices. And the type of these matching conditions are defined by the ratio of the volumes of the H volumes and vertex volumes. So it's possible to obtain directly decoupling when these vertex areas are really big and they dominate. It's possible to obtain Kirchhoff matching conditions, the most classical case, when edges dominate, and special case, it's like critical case, when the ratio of when epsilon goes to zero, the limit of the ratio of the volumes is constant, then leads to a special so-called impedance delta type matching conditions. That means that matching conditions will depend on spectral parameter Z. So that means that it's not meaningless to study such graphs, and we will for the simplicity in that talk we will consider two periodic quantum graph that consist of that contain two types of edges. Edges of different material, for example. These thick edges are stiff, so let's assume that they are stiff, and soft edges are thin. Thin edges, sorry, are soft, so that means that the corresponding second-order differential operator of these edges is OD just has the symbol epsilon square. And let's assume that the coupling condition at the vertices is a Kirchhoff or delta type, Z-dependent delta type matching condition. So this is delta type matching condition. So U is continuous through the vertex, and sum of normal derivatives is proportional to the value of the function at that vertex. In general, this coefficient alpha, it depends on z, but this dependence is linear. So just alpha times z, standard dependence is just linear, and when alpha is zero, we obtain classical Kirchhoff matching conditions. A sum of normal derivative is just zero. Because of our structure is just periodic structure, so because of that, we will start as, again, Sasha mentioned, we can start with the Gelfand transform or Flecker-Bloch, but we used Gelfand transform, and consider our operator on the fibers. So this is the operator is scaled on the fiber, means on the cell of periodicity with boundary points that are glued together. So these 2 points will go together, and that 2 points. So, and for the given example, we end up with very nice and very simple graph with 2 vertices. It depends on the boundary condition, but in general, with two vertices, natural matching condition at these 2 vertices, and 1, 2, 3, and four edges. 3 of them are stiff, and the only one is soft. So, and the idea the model operator can be constructed using boundary triples technique. So we can peak boundary triple. K will be just a finite dimensional vector space. So in our case, if he has natural conditions, that it's just two-dimensional vector space. Gamma node is the Dirichlet data of the given operator. Gamma 1 is Neumann vector of Neumann data. Corresponding value Titchmarsh matrix or function will affect the spectrum of our operator, so it has poles at the eigenvalues, and M. So in that case, M will be constructed in that way that M also reflects geometry of the graph completely. Also, we could consider possible different self-adjoint parameterization of the minimal operator A, B, and these extensions can be parameterized with the matrix B. Self-adjoint matrix B it gives us the connection between Dirichlet data and Neumann data. So in particular, Dirichlet decoupling is formally parameterized as like A infinity. So it's a Friedrich extension. Crane formula gives us a description of the resolvent of our operator AB, whereas B is just a diagonal matrix with coupling constant on the main diagonal. So that's diagonal. So it's enough to start this matrix B minus M inverse, whereas B contains all information about boundary conditions, about matching conditions of the vertices, and M is Velitich mesh matrix, and this matrix constructed in that way, it's additive via components. So it's possible to send the stiff part to the boundary condition, restrict this resolvent on the soft component only, and study restrict our problems. Our problem on the soft component and study it on soft component only. This problem will be nice because of the scaling epsilon square. This term will disappear, so it's just minus second derivative. But boundary condition will depend on Z, on the spectral parameter Z, and this function is a Kirchhoff operator. And this function, it came from Steve component. So the result of this, we end up with the resultant operator R epsilon on the fiber. That is not a resolvent of some self-adjoint operator, but it's a so-called generalized resolvent, as long as this thing is a Hergos function. So it's a generalized resolvent, and it's possible to construct the out-of-space extension. Adding some, can add some additional auxiliary Hilbert space E, construct this out-of-space extension, and then sum all such resolvents over all fibers, and the resultant operator is the effective operator to the initial problem. Now this is the main scheme. Okay. So that means that it's enough to study this boundary values. And so in our case, it's B minus M stiff. M is a Veil-Tich matrix that corresponds to a stiff component. M admits the following asymptotic, and the leading term here is B. So the leading term here is one of the order one of silent square, but this matrix has one eigenvalue that is small. It's close to zero. So we should, to the leading term, we should include B, which is of the order one, and that one, this term that also doesn't depend on epsilon. And our, for the given example, the problem on the soft component looks like that. So it's just one, just L2 on 1H on the interval from 0 to L with the vertex with non-trivial coupling conditions. And this coupling condition reflects stiff component of the underlying graph. For small z, for small frequencies, small enough, for z from the compact, it's enough to consider the leading term. We can also add the next term from the expansion, but it will not change the model. But for the big enough frequencies, for example, if z is grows as 1 over epsilon, we have to consider the next term, to include the next term also. This next term is called the first character. For larger z, we should include the next term, and so on. And it turns out that, first of all, these effective models will be in a larger and larger spaces, and properties of the effective operator maybe absolutely different. So let me illustrate it for the given example. Sorry, it's so for the leading term. For the given example, for the leading term, this is our problem with the soft component, and it's a Pavlov's function. The effective space is L2 on the soft component plus, because it's the out of space extension, plus one-dimensional additional one-dimensional subspace that fills this that fills this our stiff component. So the effective operator acts like that. It acts just like a second derivative. The operator with a constant symbol on the soft component plus this additional thing. Varphy and nu can be solved can be defined explicitly for the given graph, so they're just constant, and they fill the values of our functions at the point. Also, they connect Neumann data and Dirichlet data. So this is the effective model, and a little bit later we can we discuss the dispersion relation for that model. In the case of corrected Zollman asymptotic, in the case of next term asymptotic, we couldn't use just this first four terms of the expansions, because these functions no longer have loads, but we can replace it with a corresponding Pade approximation of the initial function b minus m. So the Pade approximation, first three terms of Pade approximation are exactly, so it's a Gergos function, and this problem is also gives us this problem also provides us with the resolvent, generalized resolvent, homogenized space. Now it's L2 on the soft H plus SU2. The effective operator on the fiber acts in that way, whereas B, now beta is a Hermitian 2 by 2 matrix, so it's no longer just a constant, it's a 2 by 2 matrix. And there are two theorems. On the stiff component, the resolvent of the initial problem is close in the normal resolvent sense to the resolvent of the effective operator at the point B at Z, whereas B at Z is Jacob function, standard Jacob function. So it's not just a spectral parameter, but some function of the spectral parameter. It's standard Jacob function. For the correct norm resolvent, we have same same estimates, but now it's wait. Sorry. Effective operator is a metric differential operator with constant coefficients, and this matrix it's not just a function; it's a matrix value at the Herglos function. Okay, let's. I have. Maybe let me let us discuss special material properties. So Victor Veselaga back in 1960s predicted metamaterial, non-standard metamaterial with non-standard properties, so-called double negative metamaterial, double negative materials. So when electric permittivity and magnetic permeability, when they are both negative simultaneously, such media would support electromagnetic waves, and such media will demonstrate non-standard properties. For example, non-standard reflection, different angle of the reflection, and so on. The question is whether do such materials even exist. And yes, it's true. It can be constructed in different ways. It can be constructed using high contrast inhomogeneous media. It can be constructed using magnetic potentials or playing with geometry of thin structures. But in general, this example of the superlens that it's layered material with standard material, material with negative index, refractive index, and it's also standard material, and such material will have no reflected waves, no diffraction limit. So Veselaga noticed that such metamaterial property is possible only for for special frequencies, for some frequencies. So electric permittivity and magnetic permeability must depend on the frequency. And if in our example, and it means the material is metamaterial in that sense if its phase velocity and group velocity are antiparallel. So that means that every individual every individual wave travels, for example, to the right, but the wave envelope travels to the left. So this group velocity shows us velocity of the envelope, and phase velocity shows us the velocity of each individual monochromatic wave. So this is in terms of dispersion relation. That means that. So let me let me start with standard dispersion relation. This is for our leading term models. For the given graph, for the leading term models, we can see this is the Jacob function, which describe the dispersion relation for the given model, and we can see that this function it's symmetric, so it's not to consider this right part of our function. It grows everywhere, so that means that the media that is described as that operator it's just standard media. Doesn't have any metamaterial properties. But let's construct exactly the same, but for the first character, for the operator that involves first character. Again, we have this is frequencies, so we have a band gap structure of the spectrum, and it looks similar to the standard Jacob function, but with some strange lines, horizontal lines. And if it looks closer, these horizontal lines, now it's not just the lines, it's small gaps in the in the band, and moreover, it's gaps is okay, but it's the operator, the limit operator, homogeneous operator, has already has already of the band gap structure spectrum, but it's also it can be noticed that this function dispersion relation it starts to decrease, and that means that the group velocity is and it's the opposite direction to the phase velocity. So here for this frequency, for this interval frequencies, the operator acts as a metamaterial. So this is an example of metamaterial properties even for in such simple examples like quantum graphs. Thank you very much for your attention.
Thank you. I think we would have time for a very short question.
So you used the term generalized resolvent. So what is do I understand it correctly? It is an operator valued function that satisfies the resolvent equation?
Yes, generalized resolvent is a result in it's a solution of the following of the problem, is a spectral problem with a boundary condition that also depends on the spectral parameter. So this function, so if this boundary condition has a Gergos function, so let me Gergos. Oh, sorry. Let me show. Can you see my screen?
Yes.
Yes. Let me return to this problem. Sorry. Yes. So